All right, so 1.5, we're going to talk about solution sets of linear systems. Now we've covered much of this ground, so it won't there's not much new here. A few new ideas, but most of it we're fairly familiar with at this point. Um, the first new idea is we want to talk about what are called homogeneous systems. So, an homogeneous system of equations is a system where all the right hand sides equal zero. Okay, that's what we mean by homogeneous. You got zeros all along those equal signs. Okay, that's what makes it homogeneous. Now, the first thing that hopefully is obvious is there is a solution to this. It's the trivial solution. 0, 0, 0 is a solution to this system. Okay, but the question remain to ask is not, is that the solution, because we know that. The question that we're interested in is, are there an infinite number of solutions, right? 0, 0, 0 could just be one of an infinite number of solutions. We're guaranteed that there's at least one solution, but are there others, which would then imply there are an infinite number? Remember, because there are only three things that can happen with the system of equations. You either have one solution, zero solutions, or infinite number of solutions. The fact that we have one solution, 0, 0, 0, eliminates the option of zero, no solutions, of course. But it doesn't eliminate the possibility of an infinite number of solutions. Okay, so that's where this becomes kind of interesting and what we want to look at. So, of course, we've learned that what we would do um, to solve this system is we would throw it uh, into its um, into its matrix, right? Into its augmented matrix. 1, 2, negative 3, 0. 2, 1, negative 3, 0. Negative 1, 1, 0, 0. And so that's what its augmented matrix would look like. Now, we could then solve this by hand, which I think it might be a good idea for you to practice doing it by hand. Get it into row reduced echelon form. When I say solve a system of equations, when it's in a matrix, what I mean is put it in row reduced echelon form. All right. So that's what you ought to do. You ought to take this opportunity to practice and do it by hand. I'm going to go ahead and give you the RREF for this thing. Okay. So the row reduced echelon form for this matrix looks like. Try that again. 1, 0, negative 1, 0, 0, 1, negative 1, 0, 0, 0, 0, 0. Okay, so some things to notice about this that you want to keep track of. All right, so the first one is this. Got an entire row of zeros right there. That tells you an infinite number of solutions, okay? So that's important, okay? So we've answered that question. There are an infinite number of solutions, but we want to know what they are. We need to write them as parametric in the right parametric form of those solutions. All right, so that we can demonstrate that there are non-trivial solutions. Just some other terminology, right? Leading term or pivot, and there's another leading term or pivot, and those represent the x sub 1 and x sub 2 columns. So x sub 1 and x sub 2 are basic variables. X sub 3 is free because it does not have a pivot in that column. Okay, so that's important. You identify that so that you can do this. X sub 3 is going to be just a free variable, a parameter. And then we're going to back substitute into the previous equations to find out, to write x sub 2 and x sub 1 in terms of s. So the second equation, this row, if I converted it to an equation, would look like this. 1x sub 2 minus 1x sub 3 equals 0. So So that tells me x sub 2 is going to equal x sub 3, or x sub 2 is going to just equal s. So there we go. We know x sub 2 also equals s. And then if we go up to the top equation, we can do the same thing again. We have that top equation is 1x sub 1 minus 1x sub 3 equals 0. So that tells me again x sub 1 equals x sub 3. So that means x sub 1 equals s. So it turns out this doesn't happen very often, but they all equal s. But x sub 3 is the free variable. So you get to choose what s is. And so the solutions, not only are they 0, 0, 0, but they are 1, 1, 1, 2, 2, 2, 3, 3, 3, negative 1.5, negative 1.5, negative 1.5. So we have an infinite number of solutions. Now, the thing we want to do is we want to write the solutions like in the proper form. And so we'll just use a generic x, no subscript, to represent the solution vector, S, S, S. But that's not really even where we want to go. What we want to do is we notice, oh, I can factor an s out of that, and so it ends up with s times 1, 1, 1. That's the proper form that we want to put it in as a parametric solution. Now, if there were two parameters, you'd have s times its vector plus t times its vector, as an example. So that's what you're going to see in this section. It's something we've kind of done before. We've just kind of added this last little piece onto it here about not expressing our answer like that, but expressing them in that way. So let me know if you have questions, and that should get you started on 1.5.